Okay, so in the previous lecture, we ended up describing work, energy, and how to work with these in different terms. Today, we're going to build on that and introduce one new type of force that we will use moving forward. So let's get the chat screen here online. Okay. So let's try to recap a little bit on what we did. A box is being moved with a velocity v by a force p, which is in the same direction as v. We have a box, velocity is v, force is p, both in the same direction, along a horizontal floor. The normal force, Fn, the kinetic frictional force, Fk, and the weight, Fg, are the other forces. Which one of the following statements is correct? P does positive work, Fn and Fk do zero work, Fg does negative work, Fn positive, Pfk zero, Fg negative, and two more options you have. I'll leave it to you. Let's see. D, B, D, D. Okay, so we seem to be between two answers, B and D. Okay. Remember, the definition of work is F dot D, which is equal to F D cosine theta in the case of constant forces. Fn and Fg are both at 90 degrees, and cosine 90 is 0, which means Fn and Fg do zero work. P is in the direction of the movement, so it does positive work. Fk is in the opposite direction, so Fk does negative work, and the correct answer is D, not B. Okay, so this was a very quick reminder of what we did in the previous lectures. And we're going to be doing a rather numerical example. Let's consider an elevator, a lift, of mass 500 kilograms, which is moving at a velocity of 4 meters per second downwards. In a distance of 12 meters and an acceleration of g over 5 meters per second square, what happened? What is its final velocity? Well, that's not difficult. We have our kinematic equations. Okay, but the question is, what is the work done on the cab by the gravitational force Fg? Now here it's not zero because it's actually in the direction of movement. So Fg is mg, mass times gravitational acceleration. So Wg is mg d cosine theta, F dot d cosine. And that gives us 500 times 9.81 times 12 meters times cosine theta. Cosine 0 is 1. And the answer we get is 500 times 9.81 times 12 is about 58,860. So 58,860 joules. Now B, during the 12-meter fall, what is the work done on the cab by the upward pull T of the elevator cable? Now it is very tempting to say just minus that. Okay. But let's not rush to conclusions and do it step by step. F equals MA. FG is down, tension is up. So FG minus T is equal to MA. Our tension is 4/5 mg. Work done by tension is TD cosine theta. And if we put it in, we will get minus 47088. So not the same as WG.
Doctor,
Okay.
how we get 4 over 5 and that's all? Can you repeat again?
Sure. So we know FG minus T is equal to MA. We know FG is simply mg minus T, M, and we are given A to be G over 5. So G over 5, which means T is equal to mg minus mg over 5, which is equal to 4 mg over 5. Just rearranging the equation.
Okay, got it.
Okay. Why cosine 180? Because tension works upwards. So it's 180 degrees. The movement is down. Direction of movement is down. Direction of the force is upward. So the angle between them is 180.
But doctor, if
yeah?
it is upward, if it is upward, it's mean 90.
How? How many
Straight.
degrees do you have in half circle?
What you are saying?
Full circle is 360 degrees.
Yes.
Half circle is 180 degrees. Quarter circle is 90 degrees. Your cab is moving down, but your force is up. So this is 180 degrees. Yeah?
Yes.
Okay, I noticed someone was asking about which chapter are we in. So according to the work plan, we should be doing chapter 8 today. But we're actually a bit late because I want to do a bit more examples, because whatever we do in this chapter is actually quite important, and we will be using it over and over again in future chapters. Okay, so I want to give it its due, give it enough amount of time. Okay.
Doctor,
Yeah.
we have a quiz about this chapter next week.
Probably yes. I don't know. I need to go back to see the course plan. Okay. So what is the network W done on the cab during the fall? Well, the network is the sum of all works done. We have our work of gravity and we have our work of tension. Gravity was 58860. Tension was minus 47088. And the result is 11772 joules. Okay. What is the cab's kinetic energy at the end of the 12-meter fall? There's more than one way to do it, but one way to do it is our final energy is whatever our initial energy is plus the work done. So our initial energy was half m, what was our initial v? 4 meters squared, 4 meters per second. 4 squared plus 11772 equals 500 divided by 2 times 4 times 4 plus 11772, 15772.
Doctor, M is what? The value
Mass.
of M. Yeah,
Mass.
yeah. I mean the value.
500.
Doctor, what's the difference between the question C and A?
A was
The
what is the
temperature
work done by
equals
gravity.
work.
So A was what is the work done by gravity only. B is what is the work done by tension only. C is what is the total work done, net work. So you add the two works of gravity and of tension.
Okay, so why you are subtract it together?
Because this was negative.
Okay. Okay, thank you.
When you add a negative and a positive number, you end up with a negative, with a negation. Okay. Reminder, when force is constant, this is very important, work is FD cosine theta, also known as F dot T, and work equals delta K, which is the net change in kinetic energy. Yeah? Okay. Skip this. Now I want to, never mind, it says 7-4, 7-4 in our book is power. I want to actually focus on this point because it's quite important and truly important in later courses as well. Work done by a spring force. This is a special application of what we have done this far. If you have already done your labs yesterday, you already know what I am talking about, a lot of what I'm talking about. If you are going to do your lab on Tuesday, you get a sneak peek. A spring force is a variable force from a spring. Now we have already done 2 or 3 examples in chapter 6 with variable forces. Okay, so we had a question where F was equal to BV. We did a lot of integrations. We had a couple of other questions. Okay, but I want to formalize it, and I noticed that a lot of students were still confused about it, so I want to dig a bit deeper in it. So we're going to focus on the spring force. A spring force is a variable force from a spring, and I'll come back to that in a second. It has a very particular mathematical form, and it turns out that many forces in nature have this form, even though they are not actual springs, but you can model them as springs. Okay, so we introduced something called Hooke's law. What is that? Imagine a spring, okay, and what happens is imagine a spring. When you're not pulling it and you're not pushing it, it's going to be in a natural position, the position it's naturally happy in. The spring is always going to end up here, okay, when you're doing nothing to it. If you have a block attached to it, and I have it horizontally, not vertically on purpose, so that there are no forces acting on it in the direction of motion, okay, you can take the midpoint of the block to be x equals 0. Okay, the reason why I choose this to be horizontal, not vertical, is because this x equals 0 is not particularly correct always when it's vertical. So, say I start pulling the spring. Now, initially, this was my x equals 0 point here. Now, when I have pushed it, this is my new point. X equals some number. Okay. Now, this pull, this extra thing that we have done, the spring, if you have ever played with a slinky or with a rubber band or with a spring, you will know that it wants to go back to where it was coming from in the first place. And what we call this is a restoring force, F restoring. So we have F extending, or the one we are actually doing, and then the spring itself wants to go back, so it's pulling the F restoration. And this force has a very, very specific format, which is F equals Kx. What does this mean? F restoring equals minus Kx. First thing first, one is positive, one is negative. So if we're pulling in this way, the spring wants to go back to where it was from. If we are pushing, then the spring is, again, in the opposite direction. It wants to come back where it came from. So it's in the opposite direction. What does this format tell me? Let me write all of this. Okay. What does this format tell me? It tells me that force is proportional to the distance pulled or pushed. Okay, so the more you pull a spring, the more difficult it is to pull it even more. Okay, otherwise, if you have played with these things, you will know it also means the more you pull it, the more your hand is going to hurt when you leave it, because the stronger it's going to come back. If you just pull it a tiny bit, it's going to come back tiny bit. If you pull it a bit more, it's going to come back harder. And if you really want to hit someone in class, you go with a really large rubber band and you go back, 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 and then it goes very strongly. Okay, the reason is because your force is proportional to the distance. So the more you pull, the higher the force. So what is the work done by spring force? We already said now in words, we need to pull harder, which means we need to apply more force. In physics terms, we say we need to apply, to do more work. So what is the work done by a spring force? Well, we know what the spring force is. F equals minus Kx, or minus Kd if you want, where d is displacement. Okay. What did we say the definition was? Work equals F dot T. Right? I have one tiny problem here. Okay. What F do I use? We said my F is equal to Kx. So at each instant in time, I have a different X, so a different force. So when I'm calculating my work, which F do I use? I cannot decide on an F. I need to consider all the Fs. So we'll be doing it using integration. Now, some of you might say, okay, wait. You spoke about a whole bunch of things. You did not speak what this K is. K is what we call a spring constant. It is a measure of the stiffness of the spring. It is a property usually of the material itself. Okay, so if you have two springs, one is harder than the other, the harder one will have a higher K value. The easier one to pull will have a lower k value. For a spring along the x-axis, we can write F equals minus kx. Yes, excellent, Ayham. So what we do is we say, okay, we know I am going from x1 to x2, and I need to consider every single force in between. So I'm going to integrate over the entire distance. So my work is going to be the integral of fx along the direction of movement. So in the x-axis, it will be fx dx. On the y-axis, it will be fy dy. On the z-axis, it will be fz dz. From my initial place to my final place. It's a definite integral. So let's plug in kx. This jumps a bit. Let's do it ourselves. Integral from xi to xf of minus fx dx substitute xi xf minus kx dx. It will become minus kx squared over 2 take the minus out from I to f. So once I put in the I and the f, I will get half kxf squared, half kxi squared minus half kxf squared. So the difference between our initial energy and our final energy. Why do we integrate? Why do we integrate? We integrate because our usual thing is given by W equals FD cosine theta. But if my F is not the same, it's dependent on position, my F is going to be different in every single instant of position. So when I am at position 1 and my force is kx, 2, 3, 4, 5, 10. Here, my force is going to be k. 2k, 3k, 4k, 5k, 10k. So if I want to substitute F here, which one of these do I substitute? K, 2k, 3k, 4k, 5k, 10k? What about 1.5k? What about 1.222k? What about 1.3279k? Between 1 and 2. Yeah, you have an infinite number of different forces. So you cannot just plug in one force. The only way to do it is to consider every single possible force, and mathematically speaking, the equivalent of that is integrating over the entire thing. So this work can be positive or negative, and that depends on the net energy transfer. Okay? The general rule is the work is positive if the block ends up closer to the relaxed position than it was initially. It is negative if the block ends up further away from x equals to 0. It's 0 if it ends up at the same distance from x equals 0. So if this is my x equals 0 point, and I am starting off here, if I come closer to this, my work will be positive. If I get further away, my work will be negative. For an initial position of the equilibrium position, xi equals 0, then my work is simply minus half kx squared, because this goes to 0. As usual, my work is equal to the net change of kinetic energies. Let's see for an applied force. Net change in kinetic energy equals final kinetic minus initial kinetic, which is equal to the applied work plus spring work. If the initial and final kinetic energies are 0. So if at the very beginning, I don't have a, oh, actually, I have an excellent example here. My initial kinetic energy is 0. My final kinetic energy is still 0. Now, yes, I did some work while I was moving, but my final kinetic energy is 0. So initial energy is 0, final energy is 0. Where did my energy go? Where did my work go? If my delta k is equal to 0, and this is equal to 0, then my applied force is equal to minus ws. All the force that I put in, okay, has been transferred to, or has been used up to do the pulling, to overcome the spring pull.
Doctor,
Yes?
why we are reversed between the kf and ki?
Where?
Not here, not here.
Here?
Yes.
Because your force is equal to minus kx, right?
Yeah.
You integrate from I to f minus kx dx. You take the minus sign out. Correct? So far?
Yes.
We agree?
Yes.
Okay. So minus xf squared over 2 minus xi squared over 2. But we have a minus sign on the outside. So it becomes minus xf squared over 2 plus xi squared over 2. So you end up with this.
Okay. Thank you.
Yeah? Okay. Let's do a numerical example. I have a spring and I have a block which is moving at velocity v in this direction on a frictionless surface. So you want to make it nice. Okay. Its mass is 0.4 kilograms. Its initial velocity is 0.5 meters per second. And its final velocity is 0 meters per second. So what's going to happen is the block is going to come, it's going to hit the spring, and it's going to keep pushing it until it finishes all its energy and it just stops. Okay. So spring constant we are given to be 750 newtons per meter. And the question is, how much will it compress the spring. Now, this is a very realistic problem. Okay, maybe not the frictionless bit, but this is usually for example, this is how an airbag in a car would work. You would have a spring in your steering wheel, and it would usually be a very high K spring, so it doesn't compress easily. And if you compress it enough, it will deploy the airbag. Okay, this is why airbags don't deploy in very, very small accidents. You need to do a rather large accident for the airbag to deploy. So there are many ways to do this, but the easiest way, because I know some of you are still thinking, okay, why are we bothering with all of this? Why don't we just use F equals ma and the kinematic equations we did in chapter 3? Because this is much easier, although it doesn't sound like it at this point in your life. The net change in kinetic energy is equal to the work done on the spring, right? Okay. The work done on the spring is its initial half kxi squared minus half kxf squared. Kxi is 0. It's already in its natural position, so this will simply go to 0. Kxf is whatever distance is we want. So my final energy, my final kinetic energy minus my initial kinetic energy. What's my final kinetic energy going to be? Anyone? No? Did I lose my internet connection? Can you hear me? Ah, okay. I have not lost my internet connection. Okay, good. Most of you said 0. Okay, correct. Why is someone outside the university trying to join? Okay, already joined. All right. So, since my final kinetic energy is equal to be 0, my equation becomes very, very simple. Kf is 0 minus Ki, the minus still comes down here. Half mvi squared is my initial kinetic energy. It's equal to the total energy going to the spring. Half kd squared. The halves cancel out. So I have half mv squared equals half kd squared. The halves go away. And my d is equal to vi square root of m over k. So now, just by knowing what's the mass of the block, the stiffness of the spring, and the initial velocity, okay, you can tell how much it's going to do any more calculations. No need for F equals ma, no need for V equals U plus AT, S equals UT plus half AT squared. You don't need all of these. You just consider, I had this much energy went into the spring, how much is it going to compress? Energy equals energy. Let's see if we can figure this out numerically. Let's do a PIQ. In designing, x equals v, no, x is position, v is velocity. X equals d. Here, how much it compresses. In designing a spring-loaded cannon, determine the spring constant required to launch a 2-kilogram ball with an initial speed of 1.2 meters per second from a position where the spring is displaced 0.15 meters from its equilibrium position. Two significant figures. No? No one? I simply put M is 2 kilograms. VI is 1.2. Distance is 0.15. And my K turns out to be, excellent, 128 newtons per meter. Yep. So to two significant figures, it is 130 newtons per meter. So the units of K is Newton per meter. I need to push 128 newtons to get 1 meter of compression or of elongation. Well, I said to 2SF. 2SF, 128 becomes 130. Because this thing is 2SF, this is 2SF, this is also 2SF, so your final answer can only be given to two significant figures. Okay. This work. We explained all of this, so okay. Let's revise everything we did on works and forces so far. Okay. Because by the end of this lecture, we're going to finish talking about power. So we're going to finish chapter 7. We're going to finalize and get in our heads the concept of work and of kinetic energy, so that on Wednesday, inshallah, we start doing potential energy and conservation of energy. And we can only do conservation of energy and conservative and non-conservative forces if we really understand the concept of work. So let's see. If we have understood everything so far, this should be a breeze. Okay. We're actually late. Section 10 has already finished half of chapter 8. So, a mountain climber pulls a package up the side of a mountain at a constant speed. So you have a mountain, a package is going up, V equals constant. Which one of the following statements is false? The net work done by all the forces acting on the package is 0 joules. The work done on the package by the normal force of the mountain is 0 joules. The work done on the package by gravity is 0 joules. The gravitational potential energy of the package is increasing. The climber does positive work in pulling the package up the mountain. I'll give you a minute to think about it. Okay, so most of you are saying D or E. I have a couple of people who are saying C. Okay, let's see. What are the forces on this? Direction of movement is this. We have pull, we have friction, We have normal force. We have gravity, which means G cosine theta is this way, and G sine theta is this way. The net work done by all, okay, and it says V equals constant, which means A equals 0. Yeah. Net work done by the forces acting on the package is 0 joules. This is correct. Because otherwise, if there was positive work, it would speed up. If there was negative work, it would slow down. Since the velocity is constant, the net work is 0. So this cannot be right. The work done on the package by the normal force is 0. This is correct. It's at 90 degrees. It's moving this way. The force is this way, 90 degrees between them. Okay. So this cannot be. The gravitational potential energy of the package is increasing as you go higher. We said the potential energy increases. So this is not correct. The climber does positive work in pulling the package. It's pulling it towards the direction of motion. So this is also correct. The only incorrect answer is this. The work done on the package by gravity is 0 joules. Why? Because if this is our box and it's moving in this direction, gravity is in this direction. So you have a cosine component and a sine component. The cosine component does 0 work as theta is equal to 90 degrees. But mg sine theta actually still does work because it's parallel to the direction of movement. Okay. Now, some of you have been asking me, why do we integrate? Why do we integrate? This is a general idea of why do we integrate. Okay. Work done by a general variable force. This is slightly, well, not out of syllabus, but it's usually assumed you know this, but let's do it anyway. We agreed that work is F dot T, right? Now, if my force is constant, okay, it will simply be a straight line, right? So I can simply take this number, F, and multiply it with this distance, D. If there's an angle, I can add a cosine theta. Easy. If, however, our force is variable, so like the spring, for example. So this would be the green line here, this. Okay? It would be this line. It's a variable force. So I cannot simply take a number and multiply it by a distance because my number changes at every single instant. I cannot do that. So what I can do is, like we did in the example of the spring, take 1, 2, 3, 4, 10. So 1, 2, 3, 4, 5, 6, 7, 8. I will take strips. And then I will increase the number of strips. Okay? So I will make the strips narrower and narrower and narrower. So instead of doing 1 to 2, I will do 1, 1.52. Then 1, 1.1, 1.2, 1.3, all the way to 2, and so on and so forth. And mathematically, what we're doing is, if we take the limit of the strips to infinity, or the width to 0, we can do an infinite number of strips. Okay. We end up with a limit where we have so many strips, we have an integration. So this is the general form of work for a variable force. F of x dx. You integrate the variable force along the direction in which it is variable. Okay. Let's see. There might be, so I have a few things here which might be actually interesting for you. This one is interesting. A 12,500 kilograms truck is accelerated from rest by a net force shown in the graph. Use the work energy theorem to determine the approximate speed of the truck when the force is removed. So we're applying this much force as in the diagram. What is its velocity due to this force? I'll give you a minute to try it out. No one? When it's so quiet here, I start wondering if I have lost my internet connection. 11.53 by someone, 12.5 by someone else. $25 by Rayan. So factor of 2 above Dina. Okay. $8.41 by Ahmed. Okay. Let's do it together. So we have a few 12.5s and a few 25s. Let's take a look. First thing first, I'm noticing that no one is complaining the numbers are not making sense, which tells me you have noticed that this is in kilonewtons, not newtons. So you have multiplied this by 1,000. So I'm very, very happy about that. You have noticed this. Okay. Mass is 12,500 kilograms. It's accelerated from rest, so V naught or U is equal to 0. And we want the speed of the truck when the force is removed. Using the work energy theorem, okay, we say all the force applies goes into kinetic energy. So what's the total force applied? Now, we could do an integration, but since this is a very nice graph, we don't need an integration because it's a triangle. So what we do is we say, okay, what is the total? Okay, we say, what is the total force supplied? What is the total work done? So we do, how much is this? 5, 6, 7, 8, 9, 10, 11, 12, 10, 11, 12, 13. No, 0, 1, 2, 3, 4. No, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so we do 13 times 150. Actually, no, 13,000 times 150 divided by 2. Okay, so 13,000 times 150 divided by 2, we get 975,000 joules. Yes? Now, all of this, since we started from rest, the initial kinetic energy was 0. So half mv squared is equal to this, all of this energy. I'm assuming no friction, no lost energy, nothing. Okay. So I will rearrange. I will multiply it by 2. I will divide it by 12,500. And then I will take the square root, and I will get 12.49, which is approximately 12.50. The people who said 25, I imagine you missed a factor of 2 somewhere. Either dividing by 2 when taking the area of the triangle, or dividing by 2 in the kinetic energy of half mv squared. But you missed a 2 somewhere. And then I will, let me do something. Those of you who are still confused, I will do it without all the extra typing. Okay. We're using the work energy theorem. Work equals net change in kinetic energy, which is half mv final squared minus half mv initial squared. What is my initial velocity? 0. The truck moves from rest, so this all goes to 0. So my work is equal to half mv final squared. We want to know what the phi final squared is. What is work? Work is the area under this graph, force distance. So it will be 13,000 times 150 divided by 2 is equal to half mvf squared. The half and the half go away. So we get 13,000 times 150 divided by 12,500 kilograms, all square rooted, will be equal to my final velocity, which is equal to 12.489, which is approximately 12.50 meters per second. Okay. Okay. Okay, let's do the final thing in chapter 7 and get it over with. Power. What is power? We've discussed work. Now we want to discuss power. And we use the term power on a daily basis anyway. Power is the time rate at which force does work. So remember at the very beginning when we said displacement? How quickly displacement happens is velocity. How quickly velocity happens is acceleration. والحين I'm using some not very new slides. Better? Okay, the 7.6, I took the screenshot from a different book. That's why it said 7.6. In your book, it is power 7.4, but you don't have all of these examples that what we did. Well, you have them, just they're not explained very well. They're just on all of these example. ما في شرح سيدة بس كل شيء تعال example وبعدين your head will hurt. So this is why I'm doing this. Okay. So we said displacement, how quickly displacement happens is velocity, right? Displacement over t, velocity. Okay, velocity over t, acceleration. Now we discussed work. Okay, so work over time, how quickly work happens is power. Okay, time rate at which force does work. The average power is you take all the work you have done divided by all the time that you spent and you get the average power. Now you might remember this, okay, to look very, very similar to this. Remember this from chapter 3? These look exactly the same. What is the instantaneous power then? If this is average power, what is the instantaneous power? We said V instantaneous is dx over dt. So P instantaneous is going to be the limit, which is dw by dt. Ta-da! Okay. Definitions are nice. How do we actually use them? Where are they useful in life? What is the unit of power? It's something you know. If you have ever changed a light bulb at home, you will have noticed on the box it says 30 watts, 60 watts, 100 watts. Okay? What is the unit of power? And it's given by a capital W, or if you want to write it in fully, then W-A-T-T. Okay? 1 watt means 1 joule per second. Okay? Now, I have included here an extra thing. It is 0.738 feet pounds per second. This is how Americans do it. Now, if you ever go on YouTube and decide to take a look and you look at American websites or American videos, you're going to see something like these, like this. Okay? We don't actually use it in our course. Okay? We stick to SI units. Okay. Another unit of power that is usually used, and this is mostly in cars or boats or engines in general, anything with an engine, okay, is the horsepower. And a horsepower has been defined, I don't know, 100 years ago or so, to be equal to 550 feet pounds per second, which is about 746 watts. Okay. Why? How did they measure that one horse is 550 blah, blah, blah? I have no idea. Okay. But people have become used to it, and it's easier when you're buying a car for them to tell you that it is 275 horsepower, 275 HP, than telling you it is about 205,000 watts or 205 kilowatts. It doesn't really make an example. You will see if you are into electronics or if you are into cars and you are following news of electric cars, okay, a lot of people are going for electric cars these days. Tesla is the world standard at the moment for electric cars, and you will notice that they actually use horsepowers and watts, both for their engines, for their capacities, for their batteries, etc. Okay, so these are all equivalent. The SI unit is the watt. Then you have an extra bit, a kilowatt hour. what is a kilowatt hour? A kilowatt hour is what you see if your parents have ever been really, really angry at you for leaving the AC on for a very long amount of time. وفاتورة الكهرباء جت كبيرة. This is what you're gonna see when they bring you the electricity bill to your face and go look. Okay, kilowatt hours. A kilowatt hour is how many kilowatts in 1 hour this device uses, and this is how electric power is measured. Okay, and it's equivalent to about 3.6 megajoules. So 3.6 times 10 to the power 6 joules. Okay. Let's solve for instantaneous power using the definition of work, which is FT cosine theta. Okay. So I'll just substitute FT cosine theta. Okay. Now F cosine theta are just numbers, so I'm going to kick them all out, and I will have F cosine theta dx over dt. What is dx over dt? Anyone remembers?
Velocity.
Excellent. It's simply velocity. So power is given by Fv cosine theta. Okay. Again, if you're interested in things like electrical engineering, electric power generation, how turbines, how motors work, you will see this definition of power, Fv cosine theta, quite often. A lot of the times this V has something to do, for example, with how quickly the turbine or the electric generator is moving. Okay. Let's see something. Engine A has greater power than engine B. Which of the following is correct? Engines A and B can do the same work, but A does it more quickly. A and B can do the same work in the same amount of time, or engine B can do more work than engine A in the same amount of time. We have an almost an equal distribution between A's and C's. Remember, we said power is how quickly work is done, right? So if engine A has more power than engine B, it means what? It means it can do, both of them can do the same work, but engine A can do it more quickly. So in 10 seconds, engine A will give you 100 joules, but engine B will give you maybe 50 joules or 60 joules. Yes, engine B can also give you 100 joules, but it's not going to take 10 seconds. It's going to take 15 seconds. Okay. The higher the power, the quicker you can supply energy or use energy. Okay. While you sleep, your body is using energy at a rate of 77 watts. لو سي كانت بالعكس صح بتكون yes كانت بتكون صح. إذا كانت C, engine A does more work than engine B in the same amount of time, كانت بتكون صح. Yes. Okay. While you sleep, your body is using energy at a rate of 77 watts. How many food calories are used during an 8-hour period, assuming you sleep for 8 hours a day? given that 1 calorie is equal to 4186 joules. So people who are trying to lose weight like me do these kind of calculations. $77 How many calories do you burn in 8-hour period? Okay, we have 3 answers so far: 710, 66, 530, another 530. Remember, okay, more 530s are coming in. Good. Remember, watt equals 1 joule per second. 77 watt equals 77 joules in 1 second, which means in 8 hours, you go 77 times 60 times 60 times 8 divided by, divided by 4186, and you get 529.7, which is approximately 530 calories. Well done to those who managed to do it. Okay, with this, we come to the end of our chapter 7. We have done quite a few examples. I hope those were useful. I'll stop recording now.